Hi, welcome. My name is Caroline Heneka. I'm a postdoc at Hamburg Observatory, or Hamburg University, and I'm also part of the Excellence Cluster Random Universe. So in this talk today, I would like to give you a teaser of my research that strives to put together both 21 centimeter intensity mapping as well as multi-line intensity mapping and galaxy surveys to probe the Epoch of Reionization, the EOR, in one consistent framework. So to start with a brief history of time and the universe, and then maybe translating this into surveys, to learn about the cosmic dawn after, well, some dark ages and a recombination that we measure with the CMB, where the first stars and galaxies actually switch on and start to ionize the medium around them in the course of reionization, I would like to advocate that in order to kind of match this gap at relatively high redshifts, where our knowledge as compared to modern galaxy surveys is still relatively low, we would need to create radio, but also near-infrared spectroscopic legacy surveys. And to do so alongside, of course, the traditional galaxy survey approach. So for galaxy surveys to measure life structure and properties of the radiating or ionizing sources during EOR, we can go and identify individual sources and measure their properties. But instead, we can also, in a way, a bit blur this picture and some emission over larger patches of the sky measure their fluctuations. This is very similar in the fashion of what the Planck satellite has been doing for the cosmic microwave background, the CMB. And you can see already here that you kind of catch up a bit more like fuzzy structures as well. But they both come, of course, with some disadvantages and advantages. To start with the advantages for the galaxy surveys. They pick up lots of information on the single sources, and we can also do nice population studies of these sources, which in a way is a more direct measurement. On the downside, especially as we push to higher and higher redshifts back in time, we can hit detection limits. We might tend to get more biased samples, for example, biased towards bright galaxies, or the brightest even. And these surveys are quite expensive because we have to go very deep and do spectroscopy and photometry of ideally many sources. If we compare this with intensity mapping or multi-line even, then we can do multi-source, multi-component measurements over large patches of the sky and get global properties of our populations, which is for example, for wide field surveys, a relatively cheap way to get information. Of course, then our single source information is very limited, or comparably limited to galaxy surveys. And as we move deeper and deeper into higher redshifts, of course, the foregrounds or interlooping lines as well become more and more of a problem, which is also partly true for galaxy surveys, where we have more and more problem with blending, for example, of sources. But as already hinted, they're kind of never complementary, single source, multi-source playing together. So why not use them together? And I'd say use them in one consistent framework that you model. And ideally also do it fast, because you want to explore quite a large parameter space, which is still partly unexplored. So in my multi-line modeling framework for reionization, I use semi-numeric reionization simulations based on 21 centimeter fast that give you a density field in the case of the parent code DEXM, also a halo catalog, ionization fields, spin gas temperature fields, and so on. And I couple this with parameterized key galaxy properties, for example, the star formation rate, in order to model different contributions to the full emission field that we measure in intensity mapping, being, for example, galactic contribution, a diffuse intergalactic medium contribution, and an even more extended scattered intergalactic medium contribution. In the case of Lyman-alpha, the simulations have this localized galactic component proportional to the star formation rate, and some radiation, of course, escaping the interstellar medium, and it ionizes the interstellar medium, and it ionizes the intergalactic medium around what I dubbed here the diffuse intergalactic medium, depending on a certain recombination rate and a gas temperature and ionization state. We get a certain degree of Lyman-alpha emission from this diffuse IgM, and we even get a more scattered component, as the Lyman-alpha is a resonant line that ventures out into the partly ionized or even mostly neutral IgM. And to start off with an application, I concentrate on a galactic contribution only, in this case for Lyman-alpha emitters, and I cross this with 21 centimeter emission maps. So I use the reionization setup based on 21 centimeter fast, and I calibrate my Lyman-alpha emitters to fit Subaru HSC narrowband observations. And crossing them at a redshift of 6.6, I plot here on top the cross correlation sigma at a certain length scale, 10 megaparsec in this case, as a function of both the neutral fraction as well as the spin temperature, or the ratio of the spin temperature to the CMB background temperature, actually. So what we can see here is that as the reionization progresses, the amplitude goes down of our cross signal, and at the same time, as we have more and more heating until we reach the so-called post-heating regime, when this ratio is 1, our amplitude goes down and becomes even more and more negative. So there's a zoom in on this region around post-heating, or on the post-heating assumption of 1, where we have negative cross correlations between our signal. So this is nice. It means we can follow the reionization progress and the IgM state by cross-correlating 21 centimeter and Lyman-alpha emitters. And in the end, by general cross-correlating 21 centimeter with Lyman-alpha. And there's one more point I would like to highlight. It's not just important to take into account the IgM state, but also the fluctuations. Because if we take the spin temperature to be constant, we actually, as you can see here at the bottom, become biased towards more negative cross amplitudes. We then, of course, will bias what we infer on reionization progress and IgM state in turn. So fluctuations are important here in the IgM. So this is a measurement at redshift 6.6, but if you want to push higher, why not take the full Lyman-alpha emission field to be able to push this boundary and learn more about the very first gas stars and galaxies that start to ionize the medium here. So for modeling these Lyman-alpha fluctuations, I take a wide field survey, set up similar to something like SPHEX or CDAM, the cosmic dawn intensity member proposed mission. And if we look here on top, we have the power spectrum as a function of scale K, and even at a redshift of 9, the detectable range of this cross signal between Lyman-alpha and 100 centimeter is quite large and far above the foregrounds. So this means we can push our measurements of reionization and the IgM state to higher and higher redshift, and we're quite robust to foregrounds and systematics using the cross. So if we look at the bottom, we basically have the same signal. It's a cross correlation coefficient, which is just a cross power spectrum normalized by the single power spectrum amplitudes, again as a function of scale K. And we see here at the redshift 10 is this characteristic dip of anti-correlation, which kind of corresponds to these ionized regions that show up as dark or bright, depending if you look at 21 centimeter or Lyman-alpha. So if we go from redshift 10 to 9, 8, and 7, as what we see that reionization progresses, our ionized regions become larger and larger, and our typical anti-correlation scales move to lower K or larger scales. So this is a relatively direct measurement of this progress. And well, how can we design these said wide field missions optimally to push our reionization or epoch of reionization measurements? So there's an upcoming study by myself and some collaborators where we look comprehensively at what's the best way actually to measure these line maps or this line tomography into the epoch of reionization. But we find, if we look at the signal to noise of, for example, Lyman-alpha, or also the cross power spectrum between Lyman-alpha and 1 centimeter, is that already quite moderate resolution requirements are enough to have high signal to noise measurements coupled with a certain sensitivity requirement. So there's lots that we can do and build actually still in the future. To conclude, I have shown you my self-consistent multi-line modeling framework for reionization that brings together intensity mapping and galaxy surveys to measure reionization progress, IgM state, and galaxy properties globally together. And to highlight some first lessons learned, it's crucial to look at the IgM state when doing these cross measurements and to also include fluctuations of IgM properties. And there's a large potential to push measurements in scale and redshift at a high signal to noise by using multi-line intensity mapping alongside. Thank you. Goodbye.